Good morning. We have discussed the noise models of resistor and different transistors, the MOS transistor and the bipolar junction transistor, as well as the diode. Now, one thing I have to mention is that when you have MOS in weak inversion, the mechanism that causes current is what? Diffusion. It is diffusion. It is like a bipolar junction transistor, and so is the noise. Okay. So in weak inversion, if a MOS transistor is operating with a current ID, again, I am looking at the saturation region. Here, saturation means where the current does not vary with VDS. Okay. Some 100 millivolts or so, that's what is going to happen. You can model the noise by using a small signal noise source as usual, and the spectral density of that noise is 2q ID. And if you want to express it in terms of GM, it is 2 kT times eta times GM. Okay. So it is similar to that of a bipolar transistor or a diode. So this is something I had not mentioned yesterday. And of course, as usual, you can transfer this to the gate voltage if you want to. Okay. Now with that, let's get back to what we were doing earlier. We were looking at this circuit. We know that this is a first order low pass filter from Vi to Vo with a transfer function 1 by 1 plus SCR. And in this case, it is convenient to model the noise of the resistor using a voltage source because the transfer function from that is the same as the transfer function from Vi. So V0 by Vn is also 1 by 1 plus SCR. So now, if you want to calculate the output noise spectral density, you have to take the spectral density of Vn, which is 4 kTr, and multiply it by the magnitude square of the transfer function, which is 4 kTr divided by 1 plus. So you have to do this with S substituted by J2 pi f, which gives you 1 plus 4 pi square f square c square r square. Okay. So it is some sort of low pass transfer function, right? It goes to 0 at f as f goes to infinity. And then the variance of this, which is also the mean square value of the output noise, is the integral of this from 0 to infinity. And what do you get if you integrate it? What is that? No, that's not. kT by c, yeah. So if you integrate this, you will get, if you just integrate this part, okay. So you can just change the variable to okay. And if you do that, what is this? This is the what is that? That's the inverse tangent. At 0, this is basically pi by 2 minus 0. Okay. So this integral comes out to be 4 kTr 1 by 2 pi Cr times pi by 2. By the way, this integral itself is worthwhile remembering. We'll come back to that later. This is 1 by 2 pi CR times pi by 2, which is 1 by 4 RC. Okay. It has dimensions of frequency. So this, you can see, this will just come out to be kT by C. Okay. So what do you think of this result? Is there anything interesting about it? Independent of? It will be independent of frequency. This is the variance, right? The variance is not dependent on frequency. It's the integral over all frequencies. Independent of R. Why is that interesting? No, but why is it even remarkable? So many things are independent of so many other things. Noise is produced by the resistor, but the variance seems to be independent of the resistor. Okay. Why does it behave like this? Why do we get a result that is independent of R? Well, noise is produced by the resistor. No, I know what happens in the algebra. So if you plot the spectral density, so one thing you should make a habit of is plotting and sketching. You get a lot of insight from there even when you cannot solve for things exactly. So let's say you have some value of resistance at low frequencies. That what did we say? This the spectral density is 4 kTr by 1 plus 4 pi square f square c square r square. Okay. So now clearly at very low frequencies the spectral density is 4 kTr. At very high frequencies it is 0. Okay. So what is the sort of point of interest here? What is the bandwidth? So this is f. Okay, again, don't confuse f and omega. So what is the bandwidth in the cyclic frequency? 1 by 2 pi RC. And what is the spectral density at that frequency? 2 kTr. It's basically this part is also 1, right? So that is the half power point. That is the 3 dB bandwidth. I mean, when we say bandwidth without saying anything else, typically we mean the 3 dB bandwidth. You can also specify other levels. So you can see that it goes to 2 kTr over there and then falls off. Now, if you had a different resistor value, let's say double that, what would happen is the bandwidth would be half. Okay. So you would have something like that. Okay. So the area under this and the area under the first one are the same, and it's true for any other value of resistor also. As the resistance increases, the low frequency spectral density increases, but the bandwidth reduces in the same proportion, and it turns out they cancel out, and the integral is always kT by C. And this kT by C can also be derived from other fundamental physics relationships. We won't get into that, but this is again worthwhile remembering. Okay. So again, as an exercise for C, which is let's say 100 femtofarad, what is the RMS value? What is the RMS value of the output noise? Please calculate it. This you can do in your head, I think. $20 millivolt. I don't think so. I don't think it's that high. Is it? Maybe it is. Huh? 0.2 millivolts. So kT is 4 times 10 to the minus 21. Again, at 300 Kelvin, it is 4.14 something. It's perfectly all right to use 4 for hand calculation. And then, how much is a femtofarad? So this is 10 to the minus 13. So this is 4 times 10 to the minus 8. By the way, this is volt square. Is the square root of that is 2 times 10 to the minus 4. Of course, it's always better to have like more recognizable units like 200 microvolts or 0.2 millivolts. Okay, that's something to just get a feel for the orders of magnitude. Okay. Any questions? Right. Power dissipation of what? This has got nothing. This is only noise, right? There is no signal here. If you apply a signal, it depends on the signal. Of the noise, yes. Of the noise, only the noise. The variance of the output doesn't depend on the resistor value. But if you are talking about power dissipation in the resistor, that depends on the signal that you apply to the filter, right? This is the power in the output signal. This is not the, don't mix it up with power dissipation elsewhere. This is just the mean square value of the output voltage. Okay. This is not the power dissipation anywhere. Okay. So this is just the mean square value of the output voltage. Power, when you talk about a signal, power just means the mean square value. That's all. Variance and mean square value are the same that I had mentioned earlier, right? So for ergodic processes, so let's say if we go back. Yeah. So you have all these different samples of the random process, x1, x2, and so on. And you can calculate the autocorrelation. Each signal is a known time domain signal. That is what is shown on the right side. Okay. And you can take the Fourier transform of that. Or you can take this expectation. This is the autocorrelation of a random process. This is the expectation, that means averaging over the ensemble weighted by the joint probability density function. For ergodic processes, this and that will be the same. Okay. Similarly, you calculate the variance, which is like you look at different instances of the random process at some instant of time, and from that you calculate the variance. Or you calculate the mean square value, which is just the power of one of these signals. The two will be the same for a class of processes known as ergodic processes. And the kind of processes that we will deal with, they're all that. Okay. So when we want to calculate variance, we just calculate, we calculate variance or mean square value, it will be the same for this type. Right, exactly. For thermal noise is an ergodic process. Okay. So which basically means that like 1,000 of you make this RC low pass filters, and you snapshot, you take a sample at a particular instant of time, all of you will get different values, and you calculate the variance from there, or just one of you take a long enough record of the output on an oscilloscope or some way of recording the output, and you calculate the power of that signal, the mean square value, you will get the same. Okay. Anything else? Any other questions? So fine. So now this is just an example of how we would calculate noise in circuits. This is a toy example, but exactly the same thing works, right? Here we have only one noise source, one transfer function. Noise spectral density times transfer function is what you get. If you have multiple noise sources, you do this for every noise source. You calculate the transfer functions, multiply by the respective transfer function, multiply the spectral densities by the respective magnitude square of transfer functions, add them all up and so on. Okay. Only thing is, you should, this is what you will be doing. You will be taking noise of one component at a time. So the different ones, different noise from different components will be uncorrelated. So you can just add up the spectral length. So let's go a little further with this to get some design principles. This is just calculation. But before I go there, what is the spectral density of the noise current of a resistor? 4 kT by R. What is the spectral density of the noise voltage of the resistor? 4 kDr. Okay. So if I want low noise circuits, should I use high resistances or low resistance? I don't know. One is inversely proportional to the resistance, the other is directly proportional. I mean, I don't know whether we will definitely encounter that. Actually, the previous one just said that it is independent of the resistor value. Now I'll go and ask how will we reduce the noise there? Because as a designer, that's what you want to do, right? You may want to, you design everything is working functionally. Only thing is the noise is higher. So now you want to realize the same function with lesser noise. What will you do? Reduce temperature. Yeah, very good. I think you should be in the other department. We'll see how to reduce temperature. That's actually a very interesting thing. Besides moving to some other place, I mean, Chennai is definitely not the where you can do this. No, everything depends on something and we can find it. I'm just asking what the answer is. We'll see. So that's why let's go back to this and say that this has the right transfer function. Okay. But the noise variance, the noise mean square value is 2 times what I want. I want to reduce it. Of course, I don't want to change the function, right? You can't say that, oh, I'll give you a low noise circuit, but it's not going to do what you want it to do, right? It has to have the same function. So what should I do? What should I do? If I want to have the noise, but I don't want to change the transfer function. Yeah, increase here, reduce R, because in this case, anyway, we have the closed form expression for the noise variance. So you double the capacitance and halve the resistance. Okay. So if you have this, or have that, the transfer function is exactly the same. Okay. But here, the output noise power is kT by C, and here, this is just a symbol for the mean square value, right? That bar means the average of this square. Okay. So this, it turns out it is a general principle. Okay. So you can do this for any circuit. I will generalize it soon, but essentially you have to reduce the impedance levels of the circuit. Now, what is really happening? So this is what is called as impedance scaling. That is, you scale all admittances by the same factor. The transfer function will remain the same. That you can easily imagine. I won't derive that. I think this may have been part of some basic electrical circuits assignments also. That is, if you have I mean, how do you analyze circuits? You write the nodal equations, right? And that has the conductance matrix. So now you can imagine if all conductances scale by the same amount and you have voltage sources, nothing really changes. Okay. So this impedance scaling, this leaves voltage transfer functions unchanged. Okay. Why is that? So let's see. The easiest way to imagine it is the following. So let's say I have some Vi. I'll again use this, but this is true for any circuit. And then I have another circuit with exactly the same input. The output will be exactly the same, excluding noise, right? And I can have any number of copies of this. Let me start with 2. So if I have 2 identical circuits with the same input, at every node, the voltage will be the same. So what is the next step I'll be taking? No. What I would do is, so this, oh, I started writing elsewhere, I guess. Okay. So if I have two circuits, some nodes, and I have some voltage input Vi, and each of them will have, let's say it has some reference node as well. So these will have, let's say, voltages V2, V3, Vn, and this will obviously have exactly the same values, right? We are not talking about noise now. Now, why I brought this up is you have this, and then let's say now I connect the corresponding nodes together. Okay. What happens to the circuit solution? What happens to the different node voltages? Nothing. No current flows. All those voltages are the same. You just connect them. But what have we done by connecting them? How is this new circuit compared to the old circuit? What has happened to the component values? So basically, the resistor has become what? Half of what it was, but maybe it's easier to think of conductances. G becomes 2G, C becomes 2C. By the way, this has got nothing to do with linear circuits. If you have a MOS transistor with W by L, it becomes a MOS transistor with 2 times W by L because you are connecting corresponding nodes in parallel and so on. So every component is parallel and the voltages do not change. So this should convince you that the voltage transfer functions do not change when you scale the impedance. This is impedance scaling, right? Now, of course, I showed it with two identical circuits. So that's why the scaling factor is an integer, but it doesn't have to be. I mean, you just scale the impedances by all the admittances by the same number, then nothing changes. It's easiest to show with two circuits connected together, but this is true for any case. Okay. So now what happens is that what happens to current transfer functions? So in this case, let me just take one of them as the output VO. I would have connected that node also. It can be anything. I mean, this is some arbitrarily designated output node. Voltage transfer functions do not change with impedance scaling. Okay. That is, you take any Vk by V naught, it doesn't change, right? What happens to current to voltage transfer function? Let's say we had, let's see, okay, maybe it's neater if I just copy this over. So let's say I had current sources instead. Okay. What happens to the voltages? Voltages will not change. But what happened to the current to voltage transfer function? What happened to the transfer function from this current source, current to the voltage? What happens? It has become half because now the input current is 2 times II, whereas the voltages have not changed. So okay. Now, in general, if you impedance scale by some factor alpha, it will go as 1 by alpha. Okay. So now, what can you say about the noise in the scaled circuit? So in the original circuit, we have noise current sources with a power spectral density of, let's say, SIK. So let's say that we represent the noise of every component with current sources. That is possible, we know, right? And the transfer function from IK to VO, that is something. So let's say HOK, right? And if you have a circuit scaled by alpha, what is the transfer function from IK to VO? What did we say? HOK by alpha. When I say circuit scaled by alpha, I mean that the admittances are multiplied by alpha. That is, capacitance becomes alpha times C and so on. Okay. What is the power spectral density of the noise current sources? When you connect multiple circuits in parallel, again, you can just think of two in parallel and then extrapolate from there. Power spectral density of the noise current sources alone, what happens? What's it? It will scale by alpha square. What happens here? So I have, actually we can just do it with two resistors. What is the noise spectral density of this? Again, let me just use the conductance form, it's more convenient. And I have another resistor G. This is 4 kTC. So now if I connect these two in parallel, what will be the spectral density of the combined noise source? 8 kTC. And it had to be, because otherwise we have inconsistency, right? Because we have a conductance 2G and this has to be 8 kTC. Why is it 8 kTC? These two are uncorrelated. So you just have to add the spectral densities. They are from two physically different resistors, right? So the power spectral density, what will it be of the noise current sources in the circuit when you connect, when you scale the impedances? It will just be alpha SIK. Okay. So what is the output noise spectral density because of this current source? SVO, the output spectral density of the output voltage because of this particular noise source. What will it be? SIK. Okay. And here also it will be the spectral density of the noise current source, which is alpha SIK times HOK by alpha square. Okay. Which is SIK times mod HOK square times 1 by alpha. Okay. Is this clear? I showed it with, I mean, you can go back to the RC filter case. I showed that if you scale the conductance and capacitance by factor of 2, you will reduce the noise variance by a factor of 2. But this is a general result. Essentially, it is like connecting many identical circuits in parallel. Okay. And of course, when you say many identical circuits in parallel, we think of scaling by integer, but it doesn't have to be an integer. It can be anything. So if you scale the admittances by a factor alpha, then your voltage noise spectral density goes down by factor alpha and your voltages remain the same. So the signal to noise ratio, the signal power divided by noise power, that goes up by a factor alpha. Okay. So this is impedance scaling. You can use this to change the noise alone without changing the function of the circuit. Okay. So in summary, we have two circuits. You can think of any component, but I'll just show these. And it has some power supply VDD Okay. So that means it's connected like that. Now I make exactly the same circuit, but with scaled conductances, capacitances, and MOS transistor widths. Okay. So earlier we had some output voltage V0 and the noise variance was something. And now we will have the same output voltage V0 and the noise power or the mean square value will be divided by alpha. Okay. So this is impedance scaling by a factor alpha. Now what else is different between these two circuits, you think? What else is different? The voltages are all the same. What else is different? What's that? Impedance. So in particular, let's say this is drawing some current Ix. What will be the current drawn here? Alpha Ix. Okay. So again, it's easiest if you think of two circuits. If you have two identical circuits, they'll have 2 times this one. Okay. So now if this is dissipating a power PD, this will be dissipating a power alpha times PD. Okay. So this reduction in noise doesn't come for free. It comes with a proportional increase in power dissipation. Okay. Is this fine? Right. So this you use in many ways. One is, of course, let's say you have designed a circuit, it satisfies the transfer function that you want, but the noise is high. Then this is sort of a, I would say, a trivial manipulation. Of course, implementing it can sometimes become difficult for large factors alpha. But if you then at that point you don't want to change anything, you only want to reduce the noise, and one way without trying to invent a new circuit. That is a different thing. That is some. I mean, you don't know whether you will be able to invent or not. Okay. Here you can just reduce the noise by some factor by paying that price, which is power dissipation. And it's also, you can use it in other ways because you have a circuit, it's usually some complex circuit with many other sub-circuits and so on. Now you can see maybe it is dissipating too much power, and then you can take some part of the circuit, you look at its noise contribution, maybe it is very low. Then you can afford to increase its noise contribution without changing the overall noise too much. What will happen then? You can reduce its power dissipation. Okay. So you can go the other way also. It's not that you only go towards reducing noise. The goal will never be to increase noise, but you may allow an increase in noise because you want to reduce the power dissipation. Okay. So both are done. This is again some standard design tool. Okay. Of course, like if none of this works, then you may have to go and think and invent new circuits which will have lesser noise or something. Any questions here on impedance scaling? So now basically this means that if you want to have low noise, in particular, if you want to have a high signal to noise ratio, you should have lower impedance values. Okay. Now I did everything with voltages here, right? I had a voltage input, voltage output, and so on. If I had a current input, current output, what would happen? Or if I look at if my output was not a voltage, if my output was a current, will this still be true or really? That's not correct, because even if you look here, let's say my output of interest was not this voltage, the same circuit, but let's say the current through this resistor for whatever reason. So what is the current flowing here? Some current, and there will be some noise. Here the current will be alpha times higher. Current will not remain the same. The power spectral density of the noise through that will be alpha times higher. Okay. So the signal power is alpha square higher, whereas the noise spectral density or noise power will be alpha times higher. So the signal to noise ratio is still alpha times higher, even if you look at the currents. Okay. Signal goes up as alpha square, noise goes up as alpha. You have voltage remains the same, the signal remains the same, and the noise goes down by factor alpha. So signal to noise ratio whether you look at voltage signals or current signals, it goes up by factor alpha. So, and it also sort of makes sense from this general principle of there is no free lunch. You spend more power and you get lower noise. Okay. Yeah. No, noise. That's all. What is noise with respect to signal? Right. It does, right? I mean, you can, I mean, if you imagine that the signal is 1 volt, then I mean, it's the absolute value of noise. See, you can increase the signal to noise ratio by either increasing the signal or reducing the noise. So that how much signal you have depends on the swing limits, etc., etc. But given the swing limit, these two will have the same swing limits anyway. They are the same circuit, right? So it's the absolute value of noise that is reducing. I mean, one will, I mean, if they have the same SNR and different noise, one also has a smaller signal level, right? So these are now two different circuits. Okay. So now it's hard to now figure out what you're comparing. Okay. Of course, you can see design is different. I mean, I could design some circuit and you could design the same function with a lower power and lower noise if you are clever enough, right? So that's not what we are comparing. We are comparing just scaling the same circuit to have lower noise. Okay. But there are fundamental relationships between power dissipation and noise that I think is part of your next assignment. You can work it out. Okay. So now let's go to his idea, which is, so let's say this circuit is operating at an absolute temperature T. Okay. Now, what did we do here? And here, of course, I have some noise power and some signal. Okay. Now, in the second circuit, I had the same signal and alpha times lower noise power. Okay. Now, let's say that I want to get the same result. I don't want to change my circuit. I want to put it in a refrigerator. Okay. So, what is that's what he said, no? This will cool the circuit. Because every noise spectral density expression seems to have absolute temperature in it. So now to get the same result, to get a noise power of VON square by alpha, okay, what should be the absolute temperature? What should be the absolute temperature? T by alpha, okay. Now, how will you do this? How will you make the circuit go to T by alpha? Remember, we are in Chennai or any one place, right? So here, let's say that the ambient temperature is T. That is, we are operating the circuit here. The temperature of the circuit is also T. Now, what do we need? We are in the same place. So the temperature outside is T. Temperature inside is T by alpha. Okay. So what is this? What is this box? It's a refrigerator, right? Okay. So now this also doesn't come for free, right? This is IX and this is consuming some power. Okay. Now inside this refrigerator, this is dissipating some power. Okay. So what should the refrigerator do to maintain that at a constant temperature? No, I know, but what is it really doing? Huh? What is it? Right. So basically you have to draw out this power PD, right? In steady state. Otherwise, I mean, if it is dissipating power and it's not drawn out, its temperature will rise up and finally will reach equilibrium with outside. Now, this is a refrigerator, right? What refrigerator does is maintains the inside at a low temperature, outside at some temperature. The temperature difference is maintained because it is drawing heat outside. And to do that, you have to do some work. Okay, some power you have to have. How much power is it? Is there some ideal refrigerator you can think of? Huh? More than PD. How much more? Have you, what do you know of an ideal refrigerator? I mean, not the kind you buy in the market. That, do you know of ideal engines? What is an ideal engine? Do you know? What is it? You've not heard of this? I think you've not taken thermodynamics, right? You're doing now. Okay. What is the ideal engine? It's called something, somebody's name. Carnot engine. So if you reverse it, it becomes a Carnot refrigerator. What is Carnot engine? You maintain some temperature difference inside and outside the engine, and you need to maintain the difference so that you get a work output. Now, if you reverse everything, you can put work input so that you can maintain this temperature difference, okay? And you calculate the efficiency and see what power you get. Now, the circuit is taking PD. See how much power you have to put into the ideal refrigerator to maintain this temperature and see what you get. It's actually an interesting result. Okay. So this, of course, is the, I don't know if it's called the Carnot refrigerator, but it's just exactly reversed Carnot engine. Okay. Now, anyway, this is not such a crazy idea. We don't do it in, I mean, consumer electronics. You don't want to, just because you want a better cell phone reception, you don't want to build a fridge around your cell phone. But for circuits that need very low absolute noise, like this very sensitive measurements, let's say radio astronomy and so on, because you're receiving signals that are so weak that you need to have very, very low noise, you will, I mean, there are actually cooled receivers and so on. Of course, that's used in niche applications where you need very, very low noise. Okay. But of course, because you have to, I mean, that whole apparatus, I mean, first of all, it's not going to approach the power efficiency of a Carnot refrigerator. Besides that, I mean, it will be bulky and so on, right? You can't make it like very compact. But yeah, by cooling, you can reduce the noise. Okay. The Carnot refrigerator is, you calculate the result and find out. Yeah, you have to go to whatever, from 300 Kelvin to 75 Kelvin. That's all. No, I mean, circuit scaling can also be difficult, right? Because if you want to scale it by a factor of 4, the circuit becomes 4 times bigger. And similarly, if you want to scale it by 100 times, it's now 100 times bigger. Now, at this point, you have to wonder whether it's easier to cool it or easier to No, I mean, these are for completely different applications, right? I mean, like I said, nobody will think of putting your phone in a fridge just to give you better reception, right? General values of alpha. No, it can be anything, right? So, no. See, the area is limited by the total area available to you. Okay. So, initial design you do with some values, and it could be completely arbitrary. Okay. For instance, I said that let's take this particular circuit. Where is that? Yeah. So let's say I arbitrarily started with 100 femtofarad capacitor, and I find that the noise is 200 microvolts. Now, what is value of alpha? It is only depends on where I started off, right? Okay. So if I wanted 2 microvolts, either I should have, of course, with enough experience, I probably knew this and would not start with a 100 femtofarad capacitor in the first place. But if I do, I'll have to scale it by a factor of 10,000, right? So it only depends on, I mean, that scaling only depends on the sort of starting value, but yeah, very large or very small also. See, this is not only for, let's say you do conceptual design and this. So let's say you have some circuit already. You have an amplifier with some noise you have been selling and this is working well and so on. Now somebody else asks you for some spec, I mean, a different specification. Maybe only the noise is different. Everything else is the same. So then you don't go and redesign everything, right? In fact, one part of engineering is to try to get out a new thing without putting in as few innovations as possible, because as I mean, every innovation brings some uncertainty. Okay. So in that case, you should see. I mean, maybe they are asking for a lower power dissipation. In which case, you see if you can, if they can accept higher noise, you just scale it. So scaling only depends on the starting value and where you want to go. That's all. There are, of course, practical limits to scaling. That is very much there. I mean, whatever you do, you're not going to get nanofarads of capacitor on a chip or microfarads and so on. Then maybe you have to change the architecture or do something else. Anything else? Yeah. Yeah, that is fine. I mean, that can happen. I mean, self-heating is a different problem. That is that has to be taken care of separately. No, that is not what is happening, right? If it's the voltage, the mean square value is not increasing. It's only the noise that is decreasing. There's a reduction in noise, right? So if you look at currents, the mean square value of currents is increasing, and the mean square value of noise is also increasing, but not as rapidly. If you look at voltages, actually it is not. Right? Okay, so this is impedance scaling, very commonly done. So there are many other scalings that you should be aware of. I'm pretty sure that you have solved this this type of problems in electrical circuits and networks. You have R, C, and L. I'll only show passive components, but it works for everything. Okay. So let's say V naught by Vi is some transfer function. Okay. Now, so if you do R by alpha, alpha C, L by alpha, then the transfer function remains the same, only the noise is changed. If you have this, let me just avoid confusion. What happens in this case? What happens in this case? No, I don't know. What will be the transfer function? That's all I want to know. Huh? I know. What will it change to? I mean, how will you analyze a circuit with L's and C's? HO? Oh, beta. Okay. Why beta square? How do you analyze this circuit? I mean, circuits with L's and C's? Laplace transform. When you have Laplace transform, what is it? Yeah. So wherever you have S, you get beta times. You had SC, you get beta times SC. You have SL, you get beta times SL. So wherever you have S, okay, maybe I could have just shown S instead of F, but basically this is frequency scaling. Okay. So there are different kinds of scaling, impedance scaling, frequency scaling, and so on. Of course, you can combine them also. Okay. Any questions about this? So these are all like design principles, right? So invariably, when you design a circuit, you will start off with something more or less arbitrary values, not completely arbitrary, and with experience it improves. But typically, I mean, after you know the basics, it's not as though you're struggling to find out what circuit it is. You know how to make an op amp. Only thing is, it will not meet something. It may not meet swing limits. It may not meet noise and things like that. So then you have to move the circuit design in the right direction. You have to move the different components in the right direction. So that's what all this will help you with. Okay. So now we have to move on. So let's say we take a slightly more complicated example. I won't worry about operating point and so on. This has some GM, VI, V naught. This is the small signal model. What is the What is the circuit? Common source amplifier. What is V0 by Vi? Minus GMR. And then I can, let's say I have a capacitor CL. So then what will be V0 by Vi? Minus GMR 1 plus SCLR. Basically, this RC combination has an impedance R by 1 plus SCR, right? RC parallel combination. So please evaluate the output noise power spectral density and output noise variance in both these circuits, and we'll continue from there. Okay, this is a very trivial extension to what we have done with RC. Huh? Yeah. Yeah, first one you can't have the variance because you can only have the, because it doesn't have band limiting. Or you just do it for the second one. The first one is the same thing with F substituted by 0. That's all. Okay, please do this. Any questions? Okay, see you all.